So, projectile motion. Sounds kind of heavy, right? A big cornerstone of physics, and it looks super complicated. But what if I told you there's just one little trick, one core idea that makes solving these problems, well, honestly, kind of simple. In this explainer, we're going to master that one idea. So let's just jump right in.
I mean, have you ever really thought about it? How physicists can predict the exact spot a football is going to land or where a cannonball is going to hit. It almost feels like magic, doesn't it? But, it's not. It's physics. And the secret behind it all is, well, it's way more straightforward than you'd think. Okay, so what are we even talking about here? What is projectile motion? Simply put, it's just any object. A baseball, a bullet, a drop of water from a sprinkler, anything flying through the air where the only thing pulling on it is gravity. Now look, to keep things simple for us, we're going to totally ignore stuff like air resistance for now. That way, we get a really clean, perfect model to play with.
Okay, you ready? This is it. This is the secret, the absolute key to getting a handle on this whole topic. You ready? You don't solve projectile motion as one big, messy, two-dimensional problem. No way. Instead, you break it apart. You split the world into two totally separate and way, way simpler one-dimensional problems.
Let's really dig into that. We call it the big split. First, think about the horizontal world, the x direction. Once something is launched, is there anything pushing or pulling it sideways? Nope. So its speed in that direction is just constant. It never changes. It's just cruising along. Simple, right? But then you've got the vertical world, the y direction, and that's a whole different story. Gravity is always pulling it down, which means its vertical speed is always changing. So you have these two completely separate stories happening at the same time. And what's the one thing that links them together? Time. The object is only flying for a specific amount of time, and that time is the one thing these two separate worlds have in common.
Okay, theory is great, but let's actually see how this works. We're going to jump into our first case study, a nice, simple horizontal launch. Think of it as mastering the basics by, throwing a rock off a cliff. Let's see this big split in action.
All right, picture this. You're standing on top of a cliff. You take a rock and you throw it straight out, perfectly flat, totally horizontal. At that exact instant you let it go, all of its speed is going sideways in that horizontal x direction. What about its vertical speed? Well, it's zero. It hasn't started falling yet. It's not moving up. It's not moving down. Not yet.
So the big question is, where is it going to land? This is where our big split comes in. First, we are going to look only at the vertical part of the problem. We just pretend the horizontal part doesn't even exist for a minute. Using a basic kinematics equation, we can figure out exactly how long that rock is falling based on how high the cliff is. That gives us the time. And that time is the key. Once we have it, we just unlock the other side of the problem. We switch over to the horizontal world, use that super simple equation, distance equals speed times time, and boom, we know how far it went. See? Two simple steps, one clear answer.
Now this is so important, I really want you to let this sink in. It does not matter if you throw that rock sideways at 5 miles an hour or 500 miles an hour. The time it takes to hit the ground below will be exactly the same. Think about that. Why? Because falling is a vertical thing. It's all happening in the y direction, and it couldn't care less about what's happening in the x direction.
Okay, so you got the horizontal launch down. Piece of cake, right? So let's level up. Let's add a little spice. What happens when we launch something at an angle? Now don't panic. The fundamental trick, that big split, is exactly the same.
This right here, this is the only new piece of the puzzle. See, when your initial speed is at some weird angle, we can't just plug it into our equations. We first have to break it down into its pure horizontal part and its pure vertical part. And how do we do that? With a little bit of basic trig, sine and cosine. You can just think of it like this. Cosine tells you how much of that speed is going sideways, and sine tells you how much is going up. Once you split that velocity into its components, guess what? We're right back in familiar territory, solving those two simple, one-dimensional problems again.
Seriously, that's it. It just looks more complicated. All we did was add one tiny little calculation right at the very beginning. After that, the process is 100% identical. You treat the horizontal stuff separately from the vertical stuff, just like we did with that rock. The core method doesn't change a bit.
So you can really boil this whole thing down to a simple 3-step recipe. Step 1, use your trig to split that initial angle velocity into its clean x and y components. Step 2, use only the y direction stuff to figure out the total time the object's in the air. And finally, step 3, take that time, pop it over to the x direction, and use it with your constant horizontal speed to find out how far it went. That's the whole game.
All right, so we've got the theory on lock, but now let's put it to the test. Let's see how this super flexible logic can be applied to some different kinds of problems you might actually see out there. Okay, check this out. This football problem is a perfect example of how flexible this whole method is. See here, we already know how far away the goalpost is. It's 22 meters. So we kind of have to work backwards. We flip the script. We start with the horizontal motion. We know the distance, we know the speed, so we can solve for the time it takes the ball to get there. Then we take that time and we plug it into our vertical equation. That tells us exactly how high the ball is when it reaches the goalpost. Is it high enough to clear the bar? If so, the field goal is good.
And this right here is probably the most important piece of advice I can give you. Don't just be a robot and memorize a formula. You gotta look at the problem. What do you know? What are you trying to find? Sometimes the key is in the vertical information first. And other times, like with that football kick, you start with the horizontal. It's like a little puzzle, a strategy game. And the big split gives you all the tools you need to win. You know, to really make this idea stick, let's actually look at the motion in pictures. Let's visualize the horizontal and vertical stories using graphs. It's just a really powerful way to see the big split in a whole new light.
First, let's look at the horizontal world. I mean, look how simple and kind of boring it is. The acceleration? It's 0. A flat line right on the axis. And because there's no acceleration, the velocity doesn't change. It's another flat, constant line. And if you're moving at a constant speed, what does your position graph look like? A perfectly straight, sloped line. It's just chugging along, steady as she goes.
But now, let's check out the much more interesting vertical world. Here, the acceleration isn't 0, it's a constant negative number, g, the pull of gravity. So you see that flat line down below the axis? And that constant downward pull is what makes the velocity graph so cool. The speed starts high, goes down, 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 hits 0 right at the very peak, and then starts increasing in the negative direction on the way down. And anytime you have a velocity that's changing at a constant rate like that, what do you get for position? You get that perfect, beautiful curve, a parabola.
So if you remember literally just one thing from all of this, let it be this. Projectile motion isn't one complicated thing, it's just two super simple things happening at the exact same time. You've got an object just coasting sideways at a perfectly constant speed, while at the same time it's falling straight down because of gravity. That's the whole trick. That's it.
And that brings us to one last really important thought. Everything we've done here, it's in a perfect physics world. But the real world, it isn't so perfect. We've completely ignored a huge real-world factor, air resistance. So the question I want to leave you with is this. How would that friction from the air mess with our nice perfect graphs? What do you think would happen to that simple constant horizontal velocity if air was trying to slow it down the whole time? Think about that, because when you do, you're already starting to think like a real physicist. Thanks for sticking with me on this one.